Have you ever wondered why a perfectly prepared weld still comes out porous, oxidized, or contaminated? In many cases, the answer is your shielding gas, or a gas that doesn't meet code. Today, we're going deep into SFA 5.32M, SFA 5.32, the ASME boiler and pressure vessel code specification for welding shielding gases, as published in Section 2 Part C of the 2025 edition. By the end of this video you'll be able to read and interpret the SFA 5.32 classification system, understand exactly what purity and dew point requirements the code mandates, know how to read a cylinder designation, and correctly select shielding gas for ASME-coded work. SFA 5.32 is titled, Welding Consumables, Gases and Gas Mixtures for Fusion Welding and Allied Processes. It is adopted from AWS specification A5.32M, A5.32, 2021, which itself is a modification of ISO 14175-2008. In case of dispute between ASME and AWS text, the original AWS text applies. Clause 1.1 lists the welding and allied processes this specification applies to. Let's read exactly what the code says. Code Ref. Clause 1.1, Processes covered. 1. Gas tungsten arc welding, GTAW. 2. Gas metal arc welding, GMAW. 3. Flux cord arc welding, FCAW. 4. Plasma arc welding, PA. 5. Plasma arc cutting, PAC. 6. Plasma arc gouging, PAG. 7. Laser beam welding, LBW. 8. Laser beam cutting, LBC. 9. Arc braze welding, ABW. 10. Electrogas welding, EGW. Importantly, the code also states that fuel gases, such as acetylene, natural gas, and propane, are not covered by this specification. And gases are always supplied and used in gaseous form, even if purchased in liquid form. The classification system in SFA 5.32 is independent of both U.S. customary units and SI. Classification is based entirely on chemical composition, not on trade names or cylinder sizes. Before diving into the classification system, let's look at Table 1 of SFA 5.32, the properties of gases. This table lists the fundamental data that drives why each gas behaves differently in the arc zone. Asterisk note: the behavior of nitrogen varies with different materials and applications. Possible influences must be considered by the user. SFA 5.32 Table 1 Footnote C. All density values specified at 0 degrees Celsius and 0.101 megapascals, 1.013 bars, 32 degrees Fahrenheit and 1 atmosphere, 14.7 Cia, Table 1 Footnote A. Notice the relative densities. Argon at 1.380 and CO2 at 1.529 are both heavier than air. This is a critical safety point. These gases can concentrate in low areas like the bottom of pressure vessels, pits, and confined spaces. The code addresses this in Annex A, Clause A8. Now we get to the heart of SFA 5.32, the classification system in Clause 5. The classification is based on the reactivity of the gas or gas mixture, not on trade names. Clause 5.1.1 states clearly, gases and gas mixtures shall be classified by the number of this standard, followed by the symbol for the gas in accordance with Table 2. There are 7 main groups. Here they are, word for word from the code. 1. I. Inert gases and mixtures of inert gases. 2. M1, M2, and M3. Oxidizing mixtures containing oxygen and/or carbon dioxide. 3. C. Highly oxidizing gas and highly oxidizing mixtures. 4. R. Reducing gas mixture, containing hydrogen. 5. N. Low reactive gas or reducing gas mixtures, containing nitrogen. 6. O. Oxygen. 7. G. Gas mixtures containing components not listed, or mixtures outside the composition ranges listed in Table 2. Table 2 in SFA 5.32 is the master classification table. It lists all main groups, subgroups, and the nominal percentage by volume of each component. Let me walk you through the most important classifications you'll encounter on ASME coded work. Note A, Table 2, for the purpose of this classification, argon may be substituted partially or completely by helium. Note B, Table 2, two gas mixtures with the same G classification may not be interchangeable. The classification gives you the main group and subgroup. The designation adds the chemical symbols and the actual percentages. Clause 5.2.1 defines the chemical symbols used. Open book code ref. Clause 5.2.1, chemical component symbols. 1. Ar, argon. 2. C, carbon dioxide. 3. H, hydrogen. 4. N, nitrogen. 5. O, oxygen. 6. He, helium. The base gas symbol comes first, followed by symbols for other components in decreasing order of percent, followed by the nominal composition values in volume percent separated by a forward slash. The G classification deserves special attention. It is used for gas mixtures containing components not listed in Table 2, or mixtures outside the composition ranges listed. Importantly, two gas mixtures with the same G classification may not be interchangeable. This is stated directly in Table 2, footnote B. Clause 6 introduces an optional supplemental designator, the letter P, which indicates that the gas mixture meets the low moisture requirements of Table 3. This P is placed as the final character of the designation, separated by a dash. Here are the two code examples for the P designator exactly as written in Clause 6. Example 1. Ar plus 30% He. Moisture less than 10.5 ppm right pointing arrow AS A5.32 I3 RE30P. Example 2 to 6% carbon dioxide, 4% O2 in AR. Moisture less than 32 ppm right pointing arrow AS A5.32 M25 ARCO 6/4 P. Clause 7 specifies that mixture tolerances apply to the volumetric percentage of the components in accordance with Table 4. This is critical for quality control on gas mixtures. Let's use the code's exact examples. For 25% CO2, the allowable tolerance is plus or minus 2.5%, giving a range of 22.5% to 27.5%. For 2.5% oxygen, the allowable tolerance is plus or minus 0.5% absolute, giving a range of 2.0% to 3.0%. Clause 8 is one of the most important clauses for code compliance. It states that the maximum dew point and purity of gases and gas mixtures shall meet the requirements of Table 5. Gas purity and moisture are specified as delivered by the supplier, not at the point of use. This distinction matters. Note A, Table 5, nitrogen, 1000 ppm maximum. CA 7.1.3 for additional information. Table 5 note, for certain applications a higher purity and or lower dew point may be recommended to avoid possible oxidation and contamination. Now let me highlight a key point from Clause 8 on testing. Sample gases for dew point analysis shall be drawn from the individual cylinder, vessel, or gas outlet source. And moisture can be expressed as concentration in ppm or as dew point in degrees Celsius at 0.101 megapascals, which is 1 atmosphere. Table 6 in the code provides the dew point conversion chart. Clause 9 covers testing. Testing of gases and gas mixtures for composition and impurity may be carried out by the manufacturer or supplier using established standards for testing and control. The code also addresses a specific situation: gases supplied in liquid premixed form. In that case, the code limits this to argon-oxygen mixes only. Clause 10 covers retesting. If any test fails, it shall be repeated twice. Both retests must pass. This is the standard ASME retesting protocol you will recognize from other material specifications. Clause 13 is critical for code compliance, certification. It states, by affixing the AWS specification and classification designations on the packaging enclosing the product, the supplier certifies that the product meets all of the requirements of the specification. This is the manufacturer's certification. The annex further clarifies what this certification means and does not mean. Clause 11 specifies exactly what must appear on the outside of each cylinder. The code requires at minimum 4 items. Clause 11 specifies exactly what must appear on the outside of each cylinder. The code requires at minimum 4 items. Here is example 1 from the code. The minimum labeling requirement to comply with SFA 5.32, Clause 11. Trade name, Tri-Mix. This product conforms to AWSA 5.32 M12 HARC 7.5, 2.5. Specific health and safety information. And example 2, a cylinder of argon meeting the P low moisture designator. XXX welding supply. Trade name, argon. This product conforms to AWSA 5.32 I1P. Specific health and safety information. Annex A of SFA 5.32 is informative, not mandatory, but it is the code's own guidance on gas selection. Clause A6 lists the factors that must be considered for proper gas selection. These are quoted directly from the code. 1. Type and thickness of base metal being welded. 2. Arc characteristics. 3. Metal transfer. 4. Travel speed. 5. Depth and width of fusion. 6. Cost of welding. 7. Mechanical properties. 8. Root opening. 9. Cleanliness of the base material. 10. Spatter. 11. Arc cleaning action. 12. Gas purity. 13. Joint configuration. 14. Welding position. 15. Fume generation. The code describes argon as a chemically inert gas used both singularly and in combination with other gases. It is used for welding nonferrous materials such as aluminum, nickel, copper, magnesium alloys, and reactive metals including zirconium and titanium. In GTAW, argon produces a constricted arc column at a high current density which causes what the code calls a distinct finger-like depth of fusion profile. The code says CO2 is an active gas used primarily for GTAW and FCAW. At arc temperatures, CO2 dissociates into carbon monoxide and free oxygen. The code is clear. Carbon dioxide cannot be used for spray transfer with GTAW. It can be used for short-circuiting and globular transfer in FCAW of carbon and stainless steel. This is important. The code explicitly states, shielding gases containing nitrogen are not recommended for welding carbon steel. Nitrogen is primarily used as a backing gas to protect the weld root. There is also a specific caution about ferrite control on stainless steels. The code states helium is used for applications requiring higher heat inputs. It has higher thermal conductivity and a wider arc column than argon. Here is a critical code statement. Using GTAW with 100% helium will only produce globular transfer. The argon percentage must be at least 20% when mixed with helium to produce and maintain a stable spray transfer. The code is direct. Oxygen is never used as a base component of a shielding gas. It can only be used as a minor component. The code notes it is used as an assist gas for cutting ferrous materials, and also as a plasma gas for plasma arc cutting. This tri-mix deserves special attention. 90% helium, 7.5% argon, 2.5% CO2. The code says this mixture is widely used for short-circuit GTAW of stainless steel in all positions. The CO2 content is kept low to minimize carbon pickup and assure good corrosion resistance, especially in multipass welds. The code includes a clear caution in Clause A6. Reactive and oxidizing gases such as carbon dioxide, CO2, and oxygen, O2, can have detrimental effects on base metals such as aluminum, nickel, titanium, zirconium, and tungsten. For this reason, carbon dioxide or oxygen cannot be used as the shielding gas for gas tungsten arc welding. Clause 14 addresses cylinder residual gases. The code requires that all gas containers shall either be evacuated, or if not evacuated, residual gases shall be analyzed for composition and purity in compliance with CGAP 15 prior to refilling. However, there are exemptions. Containers permanently equipped with a backflow prevention device are exempt, except when being filled for the first time after maintenance, or when the gas being filled is different from what was in the container. Clause 15 on packaging states gases and gas mixtures shall be packaged in accordance with DOT regulations for protection during shipment and normal storage. Cylinder sizes shall be as agreed upon between purchaser and supplier. Annex A, Clauses A5 and A8 address safety. These are informative annexes but contain important guidance. Clause A5 lists 5 factors governing fume and gas exposure during welding. Clause A8 lists specific hazards for each gas type. Let me highlight the critical ones. For argon, CO2, helium, and nitrogen, all 4 can displace oxygen in the breathing zone, potentially causing asphyxiation and death in poorly ventilated, confined work areas. The code notes that argon and CO2 are a special concern because they are heavier than air. For hydrogen, the code issues a formal warning. Hydrogen is a highly flammable gas. The code states concentrations between 4% and 75% by volume in air are relatively easy to ignite by a low-energy spark and may cause an explosion. Let's summarize the key takeaways from SFA 5.32M, SFA 5.32, 2025 edition. Summary at screen. Please review carefully. If you're doing ASME coded work involving any arc welding process, this specification is not optional, it is the code. Your welding procedure specification must reference gas classifications that conform to SFA 5.32. Your supplier's cylinder label and certificate of analysis must match. And your QC system must verify conformance as delivered, not at the point of use. If this video helped you, please like and subscribe. Drop your questions in the comments, especially if you want us to dive into specific gas classifications, how to write a WPS shielding gas section to ASME IX, or back purging requirements for pressure piping. Thanks for watching, and keep welding to code.